Recent investigations also suggest that B12 may play a role in glial cell function. Oligodendrocytes, the cells responsible for myelin production in the central nervous system, appear to require methylation-dependent signaling to proliferate and maintain function. Subtle disruptions in this system may be involved in demyelinating diseases, such as multiple sclerosis, and while the connection is not fully understood, B12 status may influence disease progression or resilience in ways not currently appreciated. There's also a whisper of intrigue surrounding B12's role in mitochondrial protection. As nerve cells are some of the most energy-demanding tissues in the body, even small improvements in mitochondrial function can have cascading effects on neuronal survival. B12 dependent enzymes, such as methylmalonyl-CoA mutase, facilitate the breakdown of certain fatty acids and amino acids into substrates usable by mitochondria for energy production. In a deficiency state, toxic intermediates like methylmalonic acid, MMA, can accumulate, impairing energy metabolism and triggering oxidative stress. This mitochondrial strain may accelerate myelin damage and neuronal aging, giving us yet another lens through which to view the quiet but profound impact of B12 insufficiency. Adding to the mystery is the fact that certain populations, especially older adults, vegetarians, and people with gastrointestinal conditions, may not absorb B12 effectively, even when intake appears sufficient. Intrinsic factor, a protein secreted in the stomach, is essential for B12 absorption in the small intestine, and its decline with age or due to autoimmune conditions can silently compromise B12 status. In this light, the nervous system becomes the canary in the coal mine. Long before anemia develops, the brain and peripheral nerves begin to show signs of strain. This raises an important and underdiscussed clinical consideration. Should neurological symptoms, especially those involving sensory disturbances or cognitive decline, prompt earlier and more aggressive investigation of B12 status? Some researchers argue that current reference ranges for serum B12 are too low to protect neural tissue, especially in vulnerable populations. Japan and some European countries set the threshold for deficiency at a much higher level than the United States, reflecting a more cautious stance toward potential subclinical nerve damage. Beyond diagnostics, this deeper appreciation for B12's role in nerve health suggests promising therapeutic avenues. High-dose B12 supplementation has shown potential in stabilizing or even reversing early-stage neuropathies, including diabetic and idiopathic forms. Methylcobalamin, a bioactive form of B12, is especially promising for neural repair and has been studied in the context of ALS and other neurodegenerative diseases. The fact that B12 is water-soluble and has no known toxicity at high doses makes it a particularly safe candidate for neuroprotection strategies, especially in aging populations. In the end, vitamin B12 may serve as a keystone in the architecture of neurological resilience. Its quiet work in preserving the integrity of the myelin sheath, preventing metabolic imbalances, and sustaining energy production reveals a molecule far more influential than its basic nutritional label implies. Far from being merely a cure for anemia, B12 appears to function as a guardian of cognitive longevity and neuronal repair, hidden in plain sight, yet essential to the silent operations of the nervous system. As research continues to illuminate its subtler roles, vitamin B12 emerges not just as a vitamin, but as a molecular defender of the mind.